Hello there, Mr. Sutton here, bringing you the BC Calculus 7-6 Part 2 homework solutions on Lagrange Error Bound. For this problem, we want to find the Lagrange Error Bound, estimating f of 0.1 for this cosine of x plus pi over 4 function with a third-degree Maclaurin polynomial. So let's set up our error bound form since they told us it's Lagrange. We have error less than or equal to big old fraction, and now my max derivative, I'm going to be going on what interval? Well, it's Maclaurin, so we're centered at x equals 0. We're plugging in 0.1, so the max from 0 to 0.1 then. And it's third degree, so that means I need fourth everything else, the next term. So this would be fourth derivative at x. And down here we have 4 factorial, and over here, since we're centered at 0, this is just going to be x to the fourth. And I don't need absolute value because it's an even exponent. All right, let me go ahead now and find my max derivative. So that's going to be, let's see, I'm going to need to actually take a few derivatives of this function here to get to the fourth derivative. So the first derivative is going to be negative sine of all this stuff. And I have a tail of 1 here. Derivative of x plus pi over 4 is just 1, so I don't have to worry about multiplying by anything over and over again. Second derivative now, we have negative cosine of this. Third derivative is going to be positive sine of all this. And my fourth derivative is going to be cosine of x plus pi over 4. So the absolute value of that is what I'm trying to maximize now. Now, cosine in general fluctuates between negative and positive 1. However, I have to look at the specific interval from 0 to 0.1, which might not get to those maximum possible values for the whole function. So cosine in general from 0 to pi over 2 is decreasing. The very first number I'm going to get when I plug in something on this interval, 0 plus pi over 4, I'm going to get pi over 4 as kind of my starting value. And cosine is decreasing until we get to an overall inside value here of pi over 2. Now, if I add 0.1 to pi over 4, I still have a number that's less than pi over 2. So I never get to this turnaround spot where I start going up again on the cosine function. So basically, cosine is decreasing along the whole interval from 0 to 0.1. This cosine function here is decreasing on this whole interval. So I want to plug in the smallest possible x value then that I can here. That's going to be 0. If I plug in 0, that's going to give me the biggest possible value of cosine, which is just the cosine of pi over 4, which is radical 2 over 2. All right, so we've found our max derivative value. So I've got radical 2 over 2 over 4 factorial, and then I'm actually plugging in 0.1 here for my x value. Let me go ahead and see what that is on the calculator. So to do this on the calculator, I did a fancy fraction inside a fancy fraction here. We have radical 2 over 2 over 4 factorial, and then 0.1 to the fourth. All comes out to about 2.94. I'm going to round this up to 7 times 10 to the negative 6. Because again, I want this stuff to be less than whatever I write over here. For this problem, we have a function with all derivatives for all real numbers, and its fourth derivative is e to the sine of x. If a third degree Taylor series about x equals 0 is used to approximate on the interval 0 to 1, what is the Lagrange error bound for the maximum area on this interval? So this is a different kind of problem, because they're not asking for Lagrange error on just like a specific number that we're plugging in. They're asking, across this whole interval, if I plug in everything on this interval, what's the biggest Lagrange error bound I can get? But we're going to start by at least writing the Lagrange error bound form for this thing, and then we'll figure out the rest. So error is less than or equal to, and now the fraction here. I'm still going to be maximizing a derivative, and the interval is going to be exactly what they gave me here, 0 to 1. I can't plug in any other values. This is the interval I care about. So max from 0 to 1. Which derivative do I need? If it's the third degree Taylor polynomial that I'm using, I need the fourth derivative on this one. And I also then need fourth factorial and x to the fourth. Now this problem is a little bit trickier because in addition to choosing the maximum derivative, which isn't really going to be any different on this problem, we also have to pick an x value because they didn't really give us one. We have to pick an x value on the interval from 0 to 1 that's going to make this thing as big as possible. But we'll cross that bridge when we get there. For now, let's start with our max derivative. Now, they already gave us the fourth derivative right up here. They just told us, hey, it's e to the sine of x. So we're trying to maximize then the absolute value of e to the sine of x. Now, the key on this one is realizing that sine is really controlling how big this thing grows, and sine itself is increasing on this interval from 0 to 1. In fact, sine in general is increasing on the interval from 0 to pi over 2. If sine were allowed to grow all the way to an input value of pi over 2, it would be as big as possible. Sine can't get bigger than 1. But we're kind of limited here. We're not allowed to get all the way to pi over 2. We're just allowed to get to 1, which is a bit shy of pi over 2. Pi over 2, and you could use a calculator to figure this out, pi over 2 is about 1.57 and some change. But since we're increasing on this whole interval from 0 to 1, that means to make sine as big as possible, we'll just plug in the biggest x value possible, which is 1 here. So this is just going to be less than or equal to e to the sine of 1. All right, so that's our max derivative. So we'll plug that in for this numerator. Now, for the max x value, to make this whole thing as big as possible, we just need to pick the biggest x value possible to plug in here. And that's going to be a value of 1. We had a choice between anything from 0 to 1, so let's plug in 1 for x. And then all this, what's this going to come out to? We need the calculator now. So plugging all this in, I'm going to use fancy fraction here. We've got e to the sine of 1 over 4 factorial. You didn't really need to write 1 to the 4th, but whatever. Press enter, and we want to write something that this is actually less than, so 0.097 would be the correct 3-decimal upper bound on this one, and that's going to be choice B. On this one, we want the Lagrange error bound approximating e to the 0.3 with this Taylor polynomial here. So on this one, since they said Lagrange error bound, let's just start with that form, error less than or equal to our fraction here. And now we have to figure out the interval that we're on. Well, you have to recognize that this is the second degree Maclaurin series for e to the x. Since it's a Maclaurin series, that means that we are centered at a equals 0, or x equals 0. So that means we have the interval from the center of 0 to the input value of 0.3, so max from 0 to 0.3. Which derivative do we need? Since it's a second degree Maclaurin series that we're using to approximate, we need 1 degree higher for everything else. So this is third derivative, third factorial, and absolute value of x to the third power. To maximize this derivative, we need to know what it is. Well, since this is e to the x, the first derivative, the second derivative, the third derivative, all the derivatives of e to the x are also e to the x. So we're just maximizing the absolute value of that. Since e to the x is an increasing function, that means we just want our x value to be as big as possible because that'll give us the biggest possible output. So then this is going to be less than or equal to e to the 0.3. Plug in some things in now. I've got e to the 0.3 for my numerator. Still have a 3 factorial down here. And now for the actual x value, we just plug in 0.3 because that's what they gave us for an actual input. And let's see what this comes out to on the calculator. So plugging all this in, we end up with about 0.006 and some change. Because I want to say that this stuff is less than something, I want to have an upper error bound, I'm going to say less than 0.007. I always round up on that third decimal. For this problem, they want the Lagrange error bound in terms of n using the nth order Maclaurin series generated by e to the x to approximate the value of e. So this one has some trickiness all around because they're not giving us a specific order, they're saying the nth order, so we're going to have to be a little more abstract here. And also figuring out the actual input value is also a little tricky. So let's start by writing the Lagrange error bound form. We have error less than or equal to our fraction here. Now what's our interval? Well, it's a Maclaurin series, so we know that this is centered at x equals 0. So we're going to be going from 0 to somewhere. And we're approximating the e to the x function for the value of e. Well, what did I plug into e to the x to get e? Well, I plugged in an x value of 1. This is kind of in the category of so easy it's hard. There's an invisible 1 here, but it's a crucial one. So this means that our interval is going to be from 0, because it's a Maclaurin series, to 1, because this is e to the 1. Which derivative do we need? We need one more than the order they gave us. Since we're using nth order, we need the n plus 1th derivative. And then that means we need n plus 1th everything else. So n plus 1 factorial. And we're also going to need x to the n plus 1 power. And I'm going to need to use absolute value because n could be anything, no pun intended. All right. And let me actually just rewrite that so that x is inside absolute value, exponent outside. At the end of the day, it won't make a difference, but this looks a little nicer. All right, so we need to go ahead now and maximize the n plus 1th derivative. Now, this seems like a daunting task because we don't really even know what n is supposed to be. But the key on this one is that they're giving you e to the x. All the derivatives of e to the x are also e to the x. So the nth plus 1 derivative of e to the x, then, is e to the x. So we're just trying to maximize the absolute value of this. So now that means I have to figure out which x value to plug in to make this as big as possible. What am I allowed to choose from? Well, my interval we said was from 0 to 1. Since e is an increasing function, I just want to plug in the biggest x value I possibly can on this interval, which is the x value 1. So this is going to be less than or equal to e to the 1, which is just e. All right, let me go ahead and plug some things back in. So this whole numerator then is just e. I still have n plus 1 factorial down here. And this is now going to be the input value of 1 to the n plus 1, and I no longer need the absolute value there. And if I wanted to, I could go ahead and simplify this because 1 to anything is just 1, so I don't need to write it there. So at the end of the day then, my error bound, error is going to be less than or equal to e over n plus 1 factorial. For number 5, we have f as a function with derivatives of all orders for all real numbers, and the third degree polynomial for f about x equals 2 is given by this t of x function here. Based off of all this, we want to start with part A by finding f of 2 and f double prime of 2. Let's start with f of 2. Now, in general, since t of x is centered at x equals 2, that means that the values of f of 2 and f double prime of 2 are actually built in to this polynomial here. So to find f of 2, that's just the constant, which is 7. And to find f double prime of 2, well, we know that the coefficient of this x minus 2 squared term is going to be equal to f double prime of 2 over 2 factorial. We know that it actually equals negative 9 in this polynomial. So that means f double prime of 2 is just going to be negative 9 times 2 factorial, or negative 18. For part B, we want to know if there is enough information given to determine whether f has a critical point at x equals 2. If not, why not? If so, is that a relative max, min, or neither? And justify your answer. So the ultimate answer to this is yes, and here's why. So to figure out whether or not we have a critical point for the function at x equals 2, we need some information about f prime, the first derivative. Specifically, we need to know if f prime is either 0 or undefined. If it is, then we have a critical point. If it's not, then we don't. What is f prime of 2 for this problem? So that's going to be the coefficient of x, but there is no x in this polynomial. Since there's no linear term, that means that f prime of 2 must be an invisible 0 that's zeroing out that linear term. So we do have a critical point, and now we just need to figure out what kind of critical point it is. For that information, probably the easiest way to do this would be to take a look at the second derivative, which we already found. We already found that f double prime of 2 was negative 18, and that tells us exactly what kind of critical point we're dealing with. Since f prime of 2 is 0 and f double prime of 2 is less than 0, that means that we're concave down, so f has a relative max at x equals 2. We're at the top of a concave down spot. For part C, we want to use t of x to find an approximation for f of 0. So let's start with that part of the problem, and then we'll get to all this other stuff. So f of 0 we can say is approximately equal to t of 0, which is all of this stuff they gave us with 0 plugged in for x. Once you've got all constants here, you actually are done with this part of the problem. You don't have to simplify. If you do end up simplifying, you're going to see that we have 7 minus, let's see, this is 36. And over here we've got minus, or actually plus 24. So 7 minus 36 is negative 29, plus 24 is negative 5. Didn't need to do that, but we went ahead and did it anyway. Next part of the problem, is there enough information given to determine if we have a critical point at x equals 0? Now, when they asked about critical points at x equals 2, we could give them anything they wanted because our polynomial here is centered about x equals 2. That means that we have perfect information about the function value and as many derivatives as we want at x equals 2. That's not the case at x equals 0. We don't know anything about the function at x equals 0 other than the function value that we just found. So the answer to this then is no. Since t of x is not centered at x equals 0, we don't know f prime of 0. For this last part of the problem, they're telling us the fourth derivative of f satisfies this inequality right here for all x's between 0 and 2. They want us to use Lagrange Error Bound, keywords here, on the approximation to f of 0 in part C, where we found that it was about negative 5. We want to use that to explain why f of 0 must be negative. Well, they said Lagrange Error Bound, so we immediately go to our Lagrange form, error less than or equal to, and now we have our fraction here. So we need an interval that we're maximizing the derivative across for this one. So we are centered for this function for this approximation at x equals 2. And we're actually plugging in 0 in this part of the problem. So that means we want the max between 0 and 2 of our derivative. Which derivative? Well, we're using this polynomial here, which is third degree, so that means we need the fourth derivative and fourth everything else. So we want fourth derivative of x, absolute value, fourth factorial, and then we're going to do x minus 2 to the fourth power, which we don't need absolute value on because this is an even exponent. Time to plug some things in now. For the max derivative at the fourth derivative, well, they actually told us that the fourth derivative is always less than or equal to 6 for all x's on the interval from 0 to 2, which is exactly the interval we're trying to maximize across. How convenient. So that means that all of this stuff up here, the biggest it can ever get is 6, because they said it was less than or equal to 6. So we've got 6 over 4 factorial, and then the plug-in value for x was 0, so this is just going to be negative 2 to the fourth out here. And this was a no calculator problem, so let me go ahead and simplify this, because I'm actually going to need to use this error bound later on, because we haven't actually answered the question. They said use it to explain why f of 0 is negative. Well, we kind of need to know what it is. All right, so trying to simplify this here, this is really going to be, let's see, negative 2 to the fourth is 16. And so that's going to be 6 times 16, which is going to be 96. And 4 factorial, I know that's 4 times 3 times 2 times 1. So that's 24. 96 over 24 is going to be just 4. So much nicer to be working with 4. All right, so how do we get to the bottom of this? Well, to figure out what f of 0 has to actually be, we have to use the fact that this error can also be expressed as f of 0 minus t of 0. Specifically, since we found t of 0 in part C to be negative 5, we can say that this error is really f of 0 minus negative 5, the absolute value of that. Now, we just found out what this error has to be. We said this error, that we can also represent this way, has to be less than or equal to 4. So this gives me an inequality I can now solve for f of 0. And by the way, I'll just write this as f of 0 plus 5. So just rewriting this without the absolute value, I can say negative 4 is less than or equal to f of 0 plus 5, less than or equal to positive 4. Now I just have to solve for f of 0. I'll do that by subtracting 5 everywhere. So I can now write negative 9 less than or equal to f of 0, less than or equal to negative 1. And since I see here that f of 0 is between two negative numbers, f of 0 must then be a negative number itself. For number 6, h is a function having derivatives of all orders for x greater than 0, and we've got some selected values of h in its first 4 derivatives in the table above. We are also told that h and the 4 derivatives are increasing on the interval from 1 to 3. So that might help us out later on. Let's keep going now for part A. We want to write the first degree Taylor polynomial for h about x equals 2, and then use it to approximate h of 1.9. And then we want to know, is this approximation greater than or less than h of 1.9? Explain our reasoning. So let's get the approximation, or the Taylor polynomial first. First degree, so the first part of our Taylor polynomial is just going to be h of 2, which we see up here is going to be 80. And then next we're going to have h prime of 2 times x minus 2. H prime of 2 is 128, so we have 128 times x minus 2. And now we need to use this to actually approximate h of 1.9, so we'll plug that in for x. And we'll say that h of 1.9 is approximately equal to my p sub 1 of 1.9 here. I don't have to simplify this, but I'm going to go ahead and do it anyway, just for the sake of argument here. So this is, let's see, negative 0.1. So then that makes this negative 12.8. 80 minus 12.8 comes out to 67.2. So there we go. Now we're not done. We have to figure out if this approximation is greater than or less than h of 1.9. So how can we figure that out? This part's actually a little tougher to get full credit on than it would seem at first glance. We have a linear approximation here, basically, and we know that the test for over or under with linear approximations is to check to see if you are concave up or down around the area of the approximation, specifically between the launching off point of the approximation, the center, which is 2 in this problem, and the actual thing you're trying to approximate, which is 1.9. So we basically have to figure out if we're concave up or down from 1.9 to 2. So how can we prove that? Well, concavity would be pertaining to h double prime. At least that's our initial idea here. So h double prime around at exactly 2, it's positive, but that's not enough by itself to show that we are concave up on the interval from 1.9 to 2. It shows that when we get finally to 2, we have a positive concavity. But how do you know, in between 1.9 and 2, whether you were positive or negative? So they gave us a little hint here. They said that the first 4 derivatives were increasing on the interval from 1 to 3. So one way you could attack this is to say, okay, at 1 we're at 42, at 2 we're at 488 over 3, which is, well, probably going to be more than 42, because 3 times 42 is definitely less than 488. So that means since we're increasing and we're positive before and after this interval that we're looking at, the concavity must be positive in between there. A faster way to do it is just simply to say, since h of prime is increasing from 1 to 3, which includes the interval from 1.9 to 2, we have to be concave up on that interval. So that's the direction I went here. Let me just write it out. Since h prime is increasing on 1 to 3, h is concave up on 1.9 to 2. So that's sufficient to prove our concavity here. And that means, therefore, since it's concave up, that our tangent line is going under the curve and is going to be an under approximation. So that means that our value p sub 1 of 1.9 must be less than h of 1.9. For part B, they want us to write the third degree Taylor polynomial for h about x equals 2 and then use it to approximate h of 1.9. So I already had the linear piece of this, which again was 80 plus 128 times x minus 2. That part's not going to change. To get the third degree Taylor polynomial, we're just going to add 2 more terms. So to get the second degree part of this, we need the derivative of h double prime of 2 times x minus 2 over 2 factorial. So that's going to end up being, let's see here, we've got 488 over 3, but we also have a 2 factorial down there, and then we have an x minus 2 squared. And then for the next one here, we have to do the third derivative at 2. So that's going to be 448 over 3 times 3 factorial now, times x minus 2 cubed. So this is our Taylor polynomial. Now we just have to approximate h of 1.9 by plugging 1.9 into all of this stuff, which you could actually just replace all the x's with 1.9 and call it a day. Or since this is the calculator section, you could come up with a decimal. I will do that now. So if I enter all that craziness in the calculator, that comes out to approximately 67.988 if I round off there. For this last part of the problem, they want us to use Lagrange Error Bound to show a third-degree Taylor polynomial about h at x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4. All right, so they said use Lagrange. Let's use Lagrange. We're going to say error is less than or equal to the following here. And now we need an interval that we're maximizing our derivative over. So we're centered at 2. We're plugging in 1.9, so we're going to find the max derivative across 1.9 to 2 for the x values. And which derivative do we need? Well, they said we're using a third-degree Taylor polynomial, so that means we need fourth derivative. And so we have h fourth prime, and then we also need 4 factorial, and we're centered at 2, so this is going to be x minus 2 to the 4th power. No absolute value needed since we have an even exponent. Now we need to find that max derivative. So taking a look at the fourth derivative here, we've got different values for the fourth derivative in this table. The key here is they said that h and the 4 derivatives were increasing on the interval from 1 to 3. So this derivative is constantly increasing as you plug in higher and higher x values. So since this is increasing on the interval from 1.9 to 2, which is part of this larger interval of 1 to 3, that means that to make h to the fourth derivative as big as you possibly can, you just need to plug in the biggest possible x value. So this fourth derivative is going to be bounded by whatever the fourth derivative is at 2. Well, what is the fourth derivative at 2? It's in the table here. It's 484 over 9. That's as big as we're going to get because we're increasing across this whole interval. And by the way, you did need to say that h fourth derivative was increasing on this interval to justify this being the biggest possible value of it. All right, now that we've done that, let's go ahead and plug some things in. So we have 584 over 9 over 4 factorial. And then my x value I'm plugging in was 1.9. So there's our whole expression here. Now, we could leave this the way it was if they just wanted the error bound, but they want us to show that the error bound is less than 3 times 10 to the negative 4. So we need to use the calculator to figure out what this comes out to numerically. So I'm just going to enter this value exactly the way it is on my calculator, and I used 2 fractions here, a Francie fraction inside a Francie fraction. Pressing enter, that comes out to about 2.704. I'm going to round up here, just so I'm guaranteed this value is less than whatever I write over here. And that was times 10 to the negative 4th power, which was also important. All right, so this approximately equal to this value. In fact, let me write less than. There we go. Now I'm still not quite done. I need to show that this is less than 3 times 10 to the negative 4th. It clearly is. 2.7 is less than 3, and we have the same 10 to the power. So I just write less than 3 times 10 to the negative 4th, and now I am done.